Welcome back to Step Electrical. Friends, we are again here to solve a numerical related to KCL and KVL, that is Kirchhoff's law. Okay, the question is, so this is the numerical problem. In this problem, there is a battery of EMF 110 volt and internal resistance of 0.2 ohm, which is connected in parallel with another battery of 100 volt and a resistance of 0.25 ohm. Then these two are connected in parallel. Now a 5 ohm resistance and 220 volt, both are connected in series, with this parallel combination. You will be clear just after watching this figure. Okay, in this figure, 110 volt is in series with 0.2 ohm resistor and 100 volt is in series with 0.25 ohm resistor, and these two branches are parallel to each other. Now this parallel combination is connected in series with 5 ohm resistor and 220 volt battery, which is the main supply. So this is the figure, and the main thing that how to tackle this problem using KCL and KVL. For this, let's see how to solve this numerical. Okay. First of all, we will redraw the circuit and assume the current. Here for the branch GC, or we can say CG, we have assumed the current I1, and for the branch FB, we have assumed the current I2. Now these two currents meet here at point A and added together, I1 plus I2 is the current which flow through this 5 ohm resistor and 220 volt main supply. So this is our first step to solve this numerical. But how to solve, how to initiate? And here first of all we have to know how many loops are there, in which loop we will apply KVL. According to selection of loops, we have categorized the solution of this numerical in first approach and the second approach. So let's see what are the loops for the first approach. Okay, in approach 1 we have A, B, F, H, G, C, A as the first loop and A, C, G, H, J, A for the second loop. We will also see what are the loops selected for approach 2. In approach 2 we have the loop A, B, F, H, G, C, A, which is common for both of this approach. And the first loop is common in both approach 1 and approach 2. But loop 2 of both approach are different. There is no more difference. Only in first loop we have taken the branch CG, but in second approach, the second loop, we have taken BF branch. And one thing that you have to understand, we can take either CG or BF for the second. There is not any difference in the magnitude and direction of the current that we will obtain as the result. So according to your wish, you can take any of the branches. You can take either this loop as the second loop or this loop as the second loop and use any approach to solve this numerical. And the last thing, while solving any numericals, we must have to think of this sign of convention, as we have discussed in KCL and KVL introduction. Once again, I want to revise that if we move from negative terminal of the battery to the positive terminal, then the potential drop across the battery is positive. If the direction of assumed current and the direction of movement for writing KVL both are in opposite direction, then the potential drop of the resistor will be also positive. And in the reverse case, for both of this battery and resistor, the potential drop will be negative. So let's move ahead and solve this numerical. Okay, now let's write KVL equation for first loop. (110 plus 0.2 I2 minus 0.25 I1 minus 100 is equal to 0. 110 volt is positive. Why? Because we are moving from negative terminal of the battery to the positive terminal. Negative terminal to positive terminal. So it is positive. For this 100 volt, we are moving from positive to negative. That's why it is minus 100. Okay, let's talk about the potential drop across these two resistors. In resistor, with resistance 0.2 ohm, the direction of assumed current I2 is in anti-clockwise direction and the direction of movement is in clockwise direction. Both are in opposite direction. If both directions are in opposite, then the potential drop is positive. So it is 0.2 I2 and positive, but this 0.25 I1 is negative. Why? Because the direction of assumed current I1 current and the direction of movement both are in same direction. That's why it is negative. Okay, on simplifying we will get 0.25 I1 minus 0.2 I2 is equal to 100. Okay, this is our first equation, and now we will write KVL equation for this second loop. (110 plus 0.2 I2 minus 220 plus 5 into I1 plus I2 is equal to 0. Here 110 volt is again positive. Why? Because movement is from negative to positive terminal of the battery. That's why it is positive, positive, negative to positive, positive. That's why 110 volt is positive. Minus 220 volt. Why? Because we are moving in this direction from positive terminal to negative terminal. That's why the potential drop across this battery is negative. Let's talk about these two resistors, 5 ohm resistor and 0.2 ohm resistor. Here for 0.2 ohm resistor, here the current I2 and the direction of current I2 is in anti-clockwise direction and the direction of this movement is in clockwise direction. Both are in opposite. In case of opposite, for the resistor the potential drop is positive, so 0.2 I2 is positive. For 5 ohm resistor, here the direction of current, assumed current, is in anti-clockwise direction and direction of movement for writing KVL, this black arrow is in clockwise direction. Both direction is again here opposite. That's why the sign here, the sign is positive. So there is potential rise. So on simplifying this, we get 5 I1 plus 5.2 I2 is equal to 110 volt, and this is linear equation. Both equations are linear. So on solving these two equations, we get I1 is equal to 32.17 ampere and I2 is equal to minus 9.78 ampere, and the total current I1 plus I2 is 22.39 ampere. Here I1 is positive but I2 is negative. It means we have assumed the direction of this I2 current in anti-clockwise direction, but the result is negative. So we have to change the direction. Magnitude will remain same, but we have to change the direction. Here we are asked to find the magnitude as well as direction. So finally we will draw the final network with corrected direction of I2. So our final figure is, okay, this is our final figure. In this figure, this I2 current is 9.78 ampere and I1 is 32.17 ampere. This current is flowing from positive to negative. It means this battery is being charged. So I1 is charging current. I2 current is 9.78 ampere, which is passing from negative to positive. That's why it is discharging current. And this is all about this numerical. Hope see you in next video. Thanks for your patience and attention.